Thanks for this great opportunity. I would like to briefly talk about our recent simulations of magnetic reconnection in the blazar environment, focusing on the optical polarization signatures. Our goal is to get a very systematic understanding of all the observables from reconnection and to study their dependence on the reconnection physics with some statistics. And as Lorenzo has already given a very nice introduction on the reconnection and the simulations, I can skip those and focus on some of the differences in our approaches. So we also use the particle in cell simulations that includes all the cooling from synchrotron and Compton scattering. And we can obtain the cell-by-cell magnetic fields and particle spectra with very good spatial and temporal resolution. The one difference here is that we use a proton-electron plasma. So although our total magnetization factor is comparable to what Lorenzo used, but the effective magnetization for the electron is much higher. So our electron can easily reach to gamma of 10 to the 4. So we do not need any extrapolation of the particle spectra. All the magnetic fields and the particle spectra information are directly taken from the particle in cell simulations. And with our simulation setup and the parameters, we do not see significant anisotropy of particles in the momentum space. And one most important feature of our simulation is that we can obtain the time, space, and frequency dependent polarized synchrotron emission, which can help us to identify key physical processes that govern the observable signatures. And also, we choose a different viewing angle. Lorenzo simulation, we are looking from the side of the simulation domain, but we are looking in front of it. So essentially, what we are seeing here is what we get from the observations. And here are 4 snapshots of our simulation output from left to right. And the 3 rows are the magnetic field strengths, the non-thermal particles at gamma 10 to the 4, and the optical polarized emission map showing the flux and the relative polarized flux and its angle. We can immediately see rich features in reconnection, including the plasmoid mergers and asymmetric plasmoid distribution in the 2 outflow directions, and highly inhomogeneous distribution of magnetic field and particles, which will lead to concentration of emission and polarized flux. And here we show the multi-wavelength signatures. The 3 panels are the light curves in optical and gamma ray bands, the optical polarization degree and angle. We have in total several tens of simulations, and the following features generally apply. One is a harder when brighter trend that applies to both synchrotron and high energy spectral components. And as we can see in the light curves, reconnection can lead to multiple flares, including some very fast flares. At the same time, the optical polarization signatures can be highly variable. In some cases, we see polarization angles once, and they are always associated to flares. The swings can go in both directions, even in one reconnection simulation, and the amplitude is typically around 180 degrees. But in some cases, the amplitude can go from about 90 degrees up to 360 degrees in our simulations. In principle, it can go even beyond that, but such events should be very rare, and the reason will be revealed in the next slide. During the swing, polarization degree typically drops. So in our setup, why we see the swings from reconnection? The reason is in this following cartoon. When the 2 plasmoid collides, because from the reconnection, all the plasmoids will have the generator will have the same orientation of its magnetic field. So when they collide at the contact region, there will be a secondary reconnection layer, which will generate a lot of new particles. And when this happened to two large plasmoids, particles accelerated in the secondary reconnection can be significant, which may dominate emission in the reconnection region. And as shown in this series of snapshots, when the two plasmoids merge on the right side here, many new particles are accelerated. Since the secondary reconnection is very similar to the primary reconnection, the two outflow directions are not always symmetric. In this case, more particles are accelerated moving up than going down. Because the post-merger plasmoid is again a semi-circular structure, the newly accelerated particles will stream along the magnetic field lines, which light up the local magnetic field structure in the polarization signatures. This will lead to both the flare and polarization angle rotation. And during this process, the particles will cool. And if they complete their stream to the other side of the post-merger plasmoid, then we see a complete 180-degree angle swing. Clearly, two key issues affect the angle rotation. One is that the particles from plasmoid merger should dominate the emission in the reconnection region. If the particles are low energy so that they do not cool fast, then the entire reconnection region is full of particles. Of course, we do not expect angle swings. The other is that we need plasmoid mergers to make swings. If mergers are rare, then there will be no swings. Of course, if the mergers are frequent, and it happens that when one merger completes a rotation, another merger event elsewhere results in a rotation in the same direction, then we expect the swing continue beyond 180 degrees. But that really needs some luck. And the longest swing we get from our simulations, it's 360 degrees. And also, one thing I want to point out here is that because we need the swings we can get here.
3 more minutes.
Sorry?
3 more minutes.
Okay, thanks. The angle swing we get here requires the particles in the two outflow directions to be very asymmetric. So it's not that all the plasmoid mergers will lead to swings. Only a small number of them will lead to swings. And now we can see how the cooling and the chance of merger can affect the polarization. Just to mention that the reconnecting magnetic field lines can have a guide field component that is perpendicular to both the inflow and outflow, which strongly affects the merger rate. As we can see in this plot with different guide field strengths, the curves with the smallest guide field stand out in the polarization angle plot. And in fact, they also have the strongest variation in both flux and polarization overall. Clearly, angle swings only happen to reconnection with very small guide fields. And in these cases, the polarization degree is generally lower during flares. Then we have a very interesting implication here, is that the blazars that have angle swings may come from reconnection with very small guide fields, so that they are generally more active in radiation and polarization than other blazars. And this figure shows the dependence on the cooling break. 3 curves represent the infrared, optical, and ultraviolet, which are before, around, and beyond the cooling break. As we can see, ultraviolet varies stronger in both flux and polarization than infrared, including large angle swings. But the average polarization degree is comparable. This is expected because higher energy electrons that make the ultraviolet emission cool faster, so that they only exist in regions with very active particle acceleration, such as the plasmoid merger sites. On the other hand, electrons from for infrared can occupy a large region in the reconnection layer. Thus, it represents the overall evolution of reconnection. And this also leads to an interesting implication that we may see strong polarization variations in the X-ray band for high frequency peak HBLS. In this plot, we compare the optical and X-ray signatures. We have several simulations available, and the X-rays can show angle swings with or without optical counterparts. Also, the X-ray polarization is much more variable than the optical band. However, this may raise troubles for IXPE because if the variation is too strong, it may not be able to resolve it. Here we consider the number of data points IXP can obtain for one event. For bright flares, if IXP can obtain several data points, then they may resolve the angle swing and the variable polarization degree. For weak ones, if IXP can only obtain one or a couple of data points, then as we can see here, the temporal depolarization effect may result in very low or undetectable polarization degree, and the angle swing cannot be resolved. Both signatures can be strong indications of reconnection in high frequency peak HBLS. And here's my summary. Thank you for your attention.